All right, welcome to lecture 5.1 covering quadratic functions. Now we just finished up looking at quadratic equations and how to solve those, and I gave you a brief preview in that lecture of how those solutions translate to the graph. So that's what we're going to be dealing with in this section is, okay, now how do we go about graphing these things? Okay, so just a bit of background information on the characteristics of parabolas. And the word parabola, that's just the name that we give to the shape that is created from a quadratic function. So that is the word parabola. Let me just get my pens going here. And I'll just point the word out to you right here, parabola. All right. So a quadratic function is a polynomial function of degree 2. So the x is squared, and the graph of the function is called the parabola. The standard form for the quadratic function, we've already seen this. We saw this standard form back in 1.6 with our toolbox or toolkit functions. So f of x is equal to a times x minus h squared plus k, where a cannot be 0. Because if a were 0, that whole square part would go away when it multiplied with the 0. Now, this is a very helpful form to have a quadratic function in, because in this form, your vertex, which is the highest or the lowest point on the parabola, the vertex shows up right here. And as a matter of fact, I've taught out of a book before that called this form vertex form. So your vertex is given by HK. So it's a very nice form to have your function written in. Now, we also have the version of the function written in the general form, and this is what we're used to seeing from solving quadratic equations. Ax squared plus bx plus c, where a, b, and c are real numbers. Now, I will say the a from here and the a from here are the same exact a's. Oh, that second one doesn't even look like an a. There we go. So, as we learned in, oh, it wasn't 1.6. I'm sorry, that's the other textbook that I'm still teaching out of. Oh, goodness, wherever we picked up the toolkit functions. We learned that this A value governs reflection about the x-axis, so in the vertical direction, and it also governs vertical stretch and shrink. So it doesn't matter which form it's in, that A is the same A in both places. So you can always tell if it's reflected and if it's been stretched or shrunk from that A value, or stretched or shrunk in the vertical direction, or stretched or compressed, rather, in the vertical direction. Okay, so the vertex from the general form is a little trickier to get, but it's not too bad. We actually have to do a little formula to figure out what the x and the y coordinates of the vertex are when it's in this general form. And to find the x coordinate, we do negative b over 2a, which is part of the quadratic formula. Hopefully that jumped out at you. And then to find the y coordinate, we just plug whatever we get in for x into the function. So f of negative b over 2a gives us that other coordinate of the vertex. So notice that the quadratic is not one-to-one. It fails the horizontal line test. And we've already looked at inverses, and so you know you have to restrict the domain of the quadratic to find its inverse. We also have some important points. We know from our last lesson, 5.1, that our x-intercepts are pretty important. They show up as solutions to the equation or if you have it in the form of a function, you plug in 0 for f of x, and that gives you your x-intercept. And then you'll also have a y-intercept. Now, you won't always have x-intercepts, and we also discovered that in the last section, and we'll look at it again here in this section. Notice, though, if you look at the parabola, it's symmetrical. I have an output value. You're always going to have double of the same output value. So here I get an output value of 4, and here I get an output value of 4. So this thing builds symmetrically away from the vertex. The line that you could imagine running vertically through the vertex is also important. It splits the parabola into two symmetrical halves. That is why it's called the axis of symmetry. And okay, so let's look. The coordinates of the vertex are 1, -4. And I have a vertical line going through that vertex. Well, we know the equation of any vertical line is x equals some value, and it's where it goes through the x-axis. It goes through the x-axis at 1, which is always going to be the same as the x-coordinate of the vertex. So we can give the formula for the axis of symmetry as either x equals h if we have it in vertex form, or x equals -b over 2a if we have it given to us in general form. So those are all of the really important pieces of the parabola that you need to know about. And when you graph a parabola, you have to have 3 points to graph a parabola. The points that you must have, you must be showing the vertex. 100%, you will never graph a parabola without graphing the vertex. And then usually we use either the x-intercepts and the y-intercept, and I know that's 4 points, but we usually use those if we have x-intercepts. If not, we just choose a value to the left of the x-coordinate of the vertex and one to the right that's the same distance away, and it gives us that shape of what our parabola is going to look like. Okay, so we're asked to determine the vertex, the axis of symmetry, the zeros. Okay, so we haven't talked about that word yet. But this is the same thing as the x-intercepts. The reason they're called zeros is because that's what you get when you plug 0 in for f of x. You have an output of 0 there. So they're called zeros, they're called x-intercepts, they're called solutions if you're dealing with an equation, and they can also be called roots. So you may hear any of those 4 words when it's referring to the x-intercept. And then it also says to locate the y-intercept. So the vertex. In this case, since my parabola is opening up, it has not been reflected. My vertex is the lowest point. and that is the point 3, 1. So my vertex is the point 3, 1. Okay, let me get another color for my axis of symmetry. My axis of symmetry is the vertical line that runs through the vertex, splitting the parabola into two symmetrical halves. And that is x equals, well, you can see it goes through 3 at the x-axis, but it also goes through the x-coordinate of the vertex. So x equals 3 is the equation for the axis of symmetry. And then the y-intercept is 7. And I don't have any x-intercepts, so my zeros, I don't have any, not applicable. Okay, so how to write the equation of the function if you're given the graph. So the first thing you want to do is identify the horizontal shift, which is going to be your h value. That's going to end up being the x-coordinate of the vertex, and your vertical shift. So all you have to do is look and see, okay, where has that vertex moved to? And that's going to be your h and your k when you're dealing with this version of the quadratic. So you're going to substitute the h and the k in there. And then all you need to do is figure out, okay, well, what's my a value? Have I reflected, stretched, or compressed? And you can figure that out by grabbing any other point on the parabola and plugging, let me get a different color actually. So you choose any other point on that parabola and you plug it in for your x and your f of x values. And then at that point, the only value that you don't have solved for is the a value. So then you just solve for a. And it says to take the absolute value of a, because remember the sign determines if it's reflected or not. The actual value of it is it's stretched or it's compressed. So if it's flipped opening downward, then we know a is negative. So positive a, we have a parabola that's opening upward. Negative a, we have one that's opening downward. And then if we're also asked to write it in general form, then we have to multiply all that out into its polynomial form. And that's what we're going to do with both of these. So on the left-hand side, it says, okay, so you're given this parabola and write the equation for it. And it says write it in general form. That's the ax squared plus bx plus c version. However, we're going to start with a times x minus h squared plus k. So the first thing we need to do is identify hk. And in this case, our vertex hk is equal to -2, -3. So far, okay, I'm going to start out with my form here. F of x equal to a times x minus h squared plus k. So far, here's what I know. I know that I've got some a value and x, f of x here. So I know minus, okay, my h value is -2. That negative is separate from the minus that's in the form, so that's going to turn into plus squared, and then my k value is -3. Okay, so I'm just going to clean this up a little bit. I have f of x equal to a times x plus 2 squared minus 3. And now I'm ready to choose any other point to plug it in to solve for my stress or compress factor, which is A. I know A is going to be positive because this thing is opening up. So I can go ahead and say at the top, since I'm opening upward, I should expect A to be positive. All right. So the point I'm going to choose, I like to choose things with zeros in them because it gets rid of things for me. So I'm going to choose the point 0, -1. And you can see it's right here. But they gave us a chart just to point out the points to us with this one. So I'm going to plug in 0, -1. So for my y value or my f of x value, I've got -1, and for my x, I've got 0. Okay, so that -1 is equal to a times 0 plus 2 squared minus 3. So now I'm just going to start unpacking everything around the a. So I'm going to isolate the a variable to know what the stretch factor is. Okay, so I will add 3 to both sides. Hopefully I won't run out of room here. I'm pushing it. Okay, so that's 2 equals a times, well, 0 plus 2 is just 2 squared. So 2 is equal to 4a. Divide both sides by 4. And I get that my a, or my stretch factor, is 1/2. A equals 1/2. All right. I am not going to have room to work this, so here's what I'm going to do. I am going to grab this problem and give myself a new page and paste that one here. Okay, and I'm going to go back and white that out so I have more room to work. Draw a white box over everything. Give me some room to work. And I gotta stick it to the page so it doesn't start moving around on me. There we go. Okay, plenty of room to work now. All right, so here's what I know now. I've got my h and my k, and I've got my stretch factor. And I know it's positive because that parabola is opening upward. So here's my equation in this standard form. F of x is equal to 1/2 times x plus 2 squared plus 3. But they ask us to write it in general form, which is ax squared plus bx plus c. So I've got to multiply all this out. So f of x equal to 1/2. I'm going to write x plus 2 times x plus 2 because I don't ever square anything in my head like that. And you shouldn't either, because 9 times out of 10 students miss that middle term when they don't write it out and do all that distribution. So better safe than sorry. This is f of x equals 1/2 times, okay, x times x is x squared, x times 2 is positive 2x, 2 times x is positive 2x, and 2 times 2 is positive 4, and then that's plus 3. So I'm just going to combine my like terms inside my parentheses. And now that 1/2 gets distributed to everything. Okay, so f of x is equal to 1/2 x squared. Okay, half of 4x is 2x. Half of 4 is 2, and then plus 3, and then my final form, f of x equal to 1/2 x squared plus 2x plus 5. There you go. Oops, that's my mark there. Let me try that again. There we go. There's your function in general form. Okay, so with this problem, it says, okay, a coordinate grid has been superimposed over this guy shooting a basketball. And it says to find the equation for the path of the ball. And you want to determine, does the shooter make the basket? So we'll consider this basketball right here living at the vertex. And let me get a yellow and draw this grid in a little bit easier so it's easier to see. Okay, so he starts shooting the basket at the origin, 0, 0. Okay, so if the basketball starts at 0, 0, then the vertex is at, let's see, negative 1, 2, 3, 4, positive 1, 2, 3, 4, 5, 6, 7. So I had to distort the picture, obviously, to get it to fit on your note sheet. So this is the point, negative 4, 7. There's my HK right there. So far, this is what I know. F of x equal to a times x minus negative 4 squared plus 7. Okay? So that's f of x equal to a times x plus 4 squared plus 7. All right, now to figure out my a value, I plug in another point. Well, conveniently, we have the point 0, 0 that we know is on the graph. So 0 equals some stretch factor times 0 plus 4. And I didn't point this out earlier, but we know that that a value is going to be negative because this parabola is opening downward. This means I have a negative a value. All right. So I'm just going to simplify. You have 0 equals a times 4 squared plus 7. I'm going to subtract 7 off of both sides. And that gives me negative 7 equals, well, 4 squared is 16, so 16a. And then divide both sides by 16. That's a yucky stretch factor, negative 7/16. Okay, so here's my function. F of x equal to negative 7/16 times x plus 4 squared plus 7. Okay, so it looks like if my ball can hit, I bet they're wanting us to use this point here because it looks like that's in the basket and that's at the crosshairs. So if this point right here makes the statement true when I plug it in, then he's going to make the basket. If it doesn't, then he won't. And we could maybe guesstimate what this point is. That might be a better one to go for, but we'll just use the one that's right on the crosshairs just for the sake of simplicity and not having to plug fractions into all this, although it would be good practice because y'all definitely need practice with fractions. All right, so let's see what this point right here is. So 1, 2, 3, 4, 5, 6, 7, 8. So negative 8, 1, 2, 3. So we're going to check the point -8, 3, and see if he makes the basket. Okay, so 3 equals -7/16 times -8 plus 4 squared plus 7. All right, 3 equals -7/16. Okay, -8 plus 4 is -4 plus 7. So I'm just simplifying down either side to see if I get the true statement. So here I have -7/16, and that's getting multiplied. Well, -4 squared is 16, which is the same thing as 16 over 1. When I work with fractions, I like for everything to look fractiony. And look here, my 16s divide out. That makes it super nice on me. And 3 equal to, okay, so all I have now is -7 plus 7. Well, -7 plus 7 is equal to 0. Aww, he's not going to make the basket. Boo-hoo. So, no, he's not going to make it. Okay, finding the vertex. So we already have this information. And notice what I put in the title there. The vertex of a parabola is also known as its maximum or its minimum, its highest or its lowest point. We'll talk a little bit more about that here in a moment. So you can find the vertex when it's in the general form, ax squared plus bx plus c, by finding your x-coordinate or your h by doing -b over 2a, and then your k is whatever you get when you plug that into the function. So the first thing I'm going to find is h, which is also the x-coordinate of the vertex, by doing -b over 2a. That's bad. Let me start over. Yeah. -b over 2a. There we go. Okay, so in this case, let me point out my a, my b, and my c. My a is 2, b is -6, and c is 7. So when I plug that in, my b and my a, I get -6 over 2 times 2, which is 6 over 4, which reduces to 3/2. And just leave it. Just leave it as 3/2 until you're done working with it. And I don't think WebAssign likes mixed numbers anyway. So just leave it as 3/2. All right. So far, here's what we know. Our vertex has an x-coordinate of 3/2. Now to find our y-coordinate or our f of x-coordinate, we just plug it in and see what we get out. So f of 3/2 is equal to 2 times 3/2 squared. Oh my goodness, students are going to have to work with fractions. Oh, however will they survive? 3/2 squared, square the top, square the bottom. That's 9/4. Okay, we can go ahead and multiply this -6 and 3/2. That's really a -6 over 1. It's a positive times a negative, so I know that that term is going to be negative. And 6 times 3, you just multiply straight across. 6 times 3 is 18. 1 times 2 is 2. And plus 7. So I'm also going to make this 2 look fractiony, so I can do that fractiony math there too. So I have 2 times 9, which is 18, over 4, minus 18 over 2, and I'm going to leave some room to get a common denominator, plus 7 over understood 1. Now I need to come back and multiply by my clever forms of 1 that give me that common denominator all the way across. Multiply fractions straight across, so 18 fourths minus 36 fourths plus 28 fourths. All right. 18 minus 36 is negative 18 fourths plus 28 fourths. And I combine my numerators over my common denominator and get positive 10 fourths, which reduces to 5 halves. That is my y coordinate, 5 halves. And that's it. They just ask for the vertex. They just want to make sure that you can do that calculation. All right, given the equation 13 plus x squared minus 6x, write the equation in general form and standard form. So the general form, we're almost there. General. That's ax squared plus bx plus c. And we start with g of x equal to 13 plus x squared minus 6x. We just need to rearrange the terms here. There's really no work to write it in general form. G of x equal to x squared minus 6x plus 13. That's it. You just have to have it as ax squared plus bx plus c. There's general form. Now I'm going to use general form to write it in standard form. I could complete the square, but I don't want to do that. Completing the square is no fun. We did that in the last section. So what I can do is figure out what my HK is from the general form, and then use that to rewrite it in standard form. I will point out, remember your A's are always the same. My A here is understood 1. So to write standard form, that is A times X minus H squared plus K. I need my A, my H, and my K. I've already got my A. I'll go ahead and write that down. My A is equal to 1. I just need to figure out the coordinates of my vertex using general form. So my vertex, the x coordinate is known as H, and that's given by negative b over 2a. And in this case, that's negative 6 over 2 times 1, which is 6 over 2 or 3. Nice. Not too bad. Okay, and my y coordinate, or my f of x coordinate, is what I get when I plug it in to the function. So g of 3 is given as 3 squared minus 6 times 3 plus 13. That's 9 minus 18 plus 13, which is negative 9 plus 13, which is 4. Okay, so I have my H, I have my K, so HK is equal to 3, 4. Now all I have to do is plug it into the form. So the standard form is g of x equals, I'm not going to write 1, it's understood to be there, x minus 3 squared plus 4. There's the general form, the standard form of my equation. Okay, domain and range of a quadratic function. You will be pleased to know, and I think I've said this in previous lectures, the domain of any quadratic function is all real numbers, negative infinity to positive infinity. If you look at both of our examples down here, they keep spreading left and right as far as the eye can see. So you don't ever have to think about the domain of a quadratic function. It's always negative infinity to positive infinity. In other words, you can square any real number you want to square, and you're going to end up with a real number. Now, let's think about the range, the output values. Notice in this parabola on the left-hand side, my vertex lives at 2, 1. And this parabola is opening up. So I could put a boundary here and know beyond a shadow of a doubt that parabola is never going to have an output value lower than 1. So if you know your vertex, if you know the k-coordinate, which is also known as the y-coordinate or the f of x coordinate of your vertex, and you know which way it's opening from its a value, you'll always know what the range is. You will know the range. It's always going to go from that y-coordinate of the vertex either into positive infinity if it's opening upward, or negative infinity if it's opening downward. So let's look at this left-hand example here. Notice my a value is positive 1. This tells me this thing is opening upward. I'm never going to go below a y value of 1. So my range, it starts at 1 inclusive and goes through positive infinity because it's opening upward. Now notice on my right-hand side, I have an a value of negative 1. That means this thing is opening downward. It's never going to go above positive 4, which is the y-coordinate of my vertex. So I come from negative infinity. Remember, you always do your lesser first and then your greater. And I'll go up 2, but will never go past 4. So as long as you know if it's reflected and you know the y-coordinate of your vertex, you can tell what the range is. The domain is always negative infinity to positive infinity. Okay, so here, find the domain and the range. Well, the domain is negative infinity to positive infinity. The domain here is negative infinity to positive infinity. All right, the range. So we need to figure out what the vertex is so we can decide what the range is. So for the vertex, for the x or the h coordinate, I need to do negative b over 2a. In this case, that's negative 9 over 2 times negative 5, which is negative 9 over negative 10, or 9/10. Doesn't really matter what my x-coordinate is, it's my y-coordinate when I'm dealing with my range that I'm interested in. So I'm actually going to have to plug in a bunch of fractions. F of 9/10 is equal to -5 times 9/10 squared, goodness, plus 9 times 9/10 minus 1. So I'm going to make everything look fractiony here. That -5's over 1 and that 9's over 1. All right. So I have -5 over 1 times 9 squared is 81, 10 squared is 100, plus 9 times 9 is 81, 1 times 10 is 10, minus 1, and I'll go ahead and put it over a 1. And I'm going to go ahead and reduce these fractions before I multiply them. 5 goes into 5 once and into 120 times. Okay, so I'm just going to rewrite to make this a little easier on the eyes. So this is basically a -1 over 1, so that's -1 times 80 over 20, so this is just -81 over 20, plus 81 over 10 minus 1 over 1. Okay, so I need to create a common denominator. I need to multiply this one by a 2 over 2 and this one by a 20 over 20. And now I have -81/20 plus, let's see, 162/20 minus 20/20. Okay, so -81 plus 162 is +81/20, and then I'm subtracting 20/20, and that gives me 61/20. So now I know, okay, so by the way, since my A value is -5, this thing is opening downward. What I know now that I have found this 61/20 value as the y-coordinate of my vertex, this thing is never going to go over or above a y value of 61/20. So my range, I come up from -infinity, and I'm going to stop at and never go above, but include 61/20. All right, this next one, we do the same thing. We've already got our domain. Now we need to find our vertex. And my h value is -b over 2a. Oh, no, I'm sorry. HK is given to us. I don't have to do any work for this one. Nice. Vertex is given in this form by HK, and that is 4/7 and 8/11. Now, the only other thing I need to point out is that I have an A of 2, so this thing opens upward, which means that that vertex sits at its minimum, and that is 4/7, 8/11. So it's going to come, it's never going to go below 8/11. So my range for this one, it starts and includes 8/11, and it goes through positive infinity because it's opening upward. Okay, determining maximum and minimum values. Well, if it opens up, you're going to have a minimum. If it opens downward, you're going to have a maximum, and those maxims and mins are always just your vertex. So to find those, you just find the y-coordinate of your vertex to know the highs or the lows. Okay, so here are the type of problems you're going to see when you're using maximum and minimum of a parabola. A backyard farmer, by the way, you will always see the word maximum or maximize or minimum or minimize when you are dealing with a quadratic and they're wanting you to find that high value or low value. You'll always see those words somewhere in the word problem. Okay, a backyard farmer wants to enclose a rectangular space for a new garden within her fenced backyard. Okay, so let me just show y'all how poor of an artist I am. And I'm going to draw a picture of this. So we have this is the fence that she's going to, let me not draw it like that. I can't draw anyway, so there's no sense in trying to make it look fancy. We'll consider this her back fence. And what she's wanting to do is section off from that back fence a rectangular garden. And so it says she has purchased 80 feet of wire fencing to enclose the 3 sides. So I have 2 widths and 1 length of fencing that I'm going to need to enclose this area. And I've got 80 feet to do that. Well, what we're talking about when we're fencing in an area is perimeter. Now notice this isn't 2W plus 2L because we don't have 2 lengths. We've only got 2 widths and 1 length. So what I know from this information is that 80 has to equal 2 times my width plus 1 length. That's what I need to get, 80. Out of that 80 feet of fencing. Find a formula for the area. Notice this is perimeter. This is the only information we have. And we're going to try to figure out how to write a formula for the area. You know, area of a rectangular solid is length times width. So what we need to do is use the perimeter formula to solve for one of the variables so that we don't have 2 variables happening in our formula. Find the formula for the area enclosed by the fence if the sides of fencing perpendicular to the existing fence have length L. Okay. Okay, it's a perpendicular to the, okay, so actually the way they have the problem set up, and it's not wrong the way we set it up, but it's best to follow what they've said. They're calling the sides perpendicular to the fence the length, and then this is the width. So we have 2 lengths and 1 width. All right. What dimensions should she make her garden to, here we go, maximize the enclosed area? So what we're going to end up doing, since we're going to be multiplying to create the area, we're going to create a quadratic formula, or not a quadratic function. And we're going to have to find the vertex of that quadratic to know what's the maximum area she can enclose. So what I'm going to do with my perimeter is just solve for one of my variables. And the easiest one to solve for is the width. I'm just going to subtract the length, 2 times the length off of both sides. And I get 80 minus 2 times 2, sorry, 80 minus 2 times the length is equal to my width. Let me show you why I did that. Now, I can come up to my diagram that I've drawn, and I can say, well, I can rename this width and actually call it 80 minus 2 times the length. And now look, all my sides are in L's. I don't have two variables happening. I've got everything in terms of length here. So I move down to my area formula, which, since I'm putting everything in terms of length, every point that I come up with is going to be in the form of length and then the function of the length, which is also known as the width. No, I'm sorry, that's the area. Length, and then this is area. Okay, so my area, which is the function of my length, is equal to my length, which is L, times my width, which I can now call 80 minus 2L. Here's why this is in the section on quadratics. Because when I multiply my length and my width, I end up getting 80L minus 2L squared. So if I flip-flop that around, f of L, or my area, is equal to negative 2L squared plus 80L. Now, let me point something out to you. Notice my A value here, not my area, but my A from AX squared plus BX plus C is negative 2. That thing is opening downward. So when I find my vertex, I am finding the maximum area. So it needed to open downward so that I'm finding a maximum. All right, so that's what I'm going to do. I just need to find the coordinates of my vertex, and I need the y coordinate or the f of L coordinate to know what that maximum area is. By the way, this right here, this f of L right here, this is that equation that they were asking. Well, no, rather we should put it in standard form, so it's the next one. This is the equation or the formula that they're asking for in Part A. Find a formula for the area enclosed. That's a formula that gives you the area. Now we need to find about maximizing it. So my H coordinate, which is the X coordinate of my vertex, my H, is equal to negative B over 2A. Okay, so B is 80, so negative 80 over 2 times negative 2, which is negative 80 over negative 4, which is 20. So far I know 20. That's going to be the length that gives me my maximum area. And then I plug that in to my width, my formula for width, to find out the other dimension, but I plug it into my function. So I do f of 20 to find out what that maximum area is. So negative 2 times 20 squared plus 80 times 20. All right, 20 squared is 400. So this is negative 2 times 400. And 80 times 20 is 1600. So plus 1600. This is negative 800 plus 1600. 800 square feet is what she can enclose. Okay, so let me point everything out to you. Actually, we need to find out what our width is. So our width is going to be 80 minus 2 times my length, which is 20. My width is going to be 80 minus 40, which is 40. Okay, so 40. All right, so let me get a completely different color and point out everything you need to know and what it means. Okay, so we have the formula. We know we've answered that first question. There's our formula right there. The second question B says, what dimensions should she make her garden? The dimensions are 20 by 40. So she has a length of 20 and a width of 40. And the maximum area that she can enclose with 80 feet of fencing is 800 square feet. That's it. Okay, so we actually talked about this next concept briefly in 5.1, and now we're just solidifying that knowledge about X and Y intercepts. I must have missed something there. We also need to find intercepts for quadratic equations for graphing parabolas. Recall that we find the y-intercept of a quadratic by evaluating the function at an input, so an x value of 0, and we find the x-intercept at locations where the output is 0 as well. So to find intercepts, you always plug in 0 for the opposite coordinate of what you're looking for. Okay, so once again, we may not have x-intercepts. That thing may be floating up. And in this case, if we solve the equation, we get complex or imaginary solutions when we can't tell where that thing has crossed the x-axis because it doesn't. We may have one solution, and we may have two solutions. And the discriminant can give us an idea of what to expect with those. That was in section 5.1 that we discussed that. Okay, so we're just asked here to find the y and the x-intercept. So we'll start with the y-intercept because that one's easier to find. So for the y-intercept, you want to plug in an x value of 0. So f of 0 equal to 3 times 0 squared plus 5 times 0 minus 2. Pretty nice and neat, huh? 0 plus 0 minus 2, negative 2. I have a y-intercept of negative 2. That is the point 0, negative 2. You can give it in either form, but make sure you look and see what form they're asking for. And you do just the opposite for the x-intercept. You plug in 0 for y, or f of x. So 0 equals 3x squared plus 5x minus 2. Okay, we have a quadratic equation we have to solve here. This can be solved by factoring. Let me just make sure. Positive 6. Yes. Okay, so I'm going to use the AC method to factor this. A is 3. C is negative 2, which gives me negative 6. I'm looking for what multiplies to make negative 6, but adds to make positive 5, and that is positive 6 and negative 1. I'm going to rewrite busting up my BX term. 0 equals 3x squared. I don't write plus 5x, I write plus 6x minus understood 1x minus 2. And now I factor by grouping. So there's a GCF of 3x here. And I'm left over with x plus 2. There is a GCF of negative 1 here. And I'm left over with x plus 2, and that's still equaling 0. So I have 0 equals, my GCF now is x plus 2, and my leftover is 3x minus 1. So I use my zero product property, x plus 2 equals 0, so x is negative 2. And 3x minus 1 equals 0, add 1, so 3x is 1, divide by 3, x is 1/3. So I have two x-intercepts with this particular problem here. I have one at negative 2 and one at positive 1/3, and here's my y-intercept information right there. Okay. So we found the general form of this equation. Oh yeah, we have found that. Let me go back so we don't have to worry about finding, or I guess we don't really need that. We can plug in zeros and not need that. Okay, so we want to find the y and the x-intercepts, if it has any x-intercepts. We'll start with the y-intercept. Okay, so the y-intercept is what you get when you plug in 0 for x. This is the easy one. So g of 0 equals 13 plus 0 squared minus 6 times 0. So that's 13 plus 0, which is just 13. My x-intercepts are a little trickier. That's what I get when I plug in 0 for y, or also known as f of x. In this case, g of x. All right, so 0 equals 13 plus x squared minus 6x. I'm going to rearrange this to standard form. X squared minus 6x plus 13. 13's prime, so this thing's not going to factor. So I'm going to use the quadratic formula to solve. X equals opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2a. So 6 plus or minus the square root of 36 minus, let's see, 13 times 4. I think we might have imaginary. Yep. We don't have to go any further than this, because when you subtract 52 from 36, you get negative 16. And I don't care to know, those aren't x-intercepts, because this is an imaginary number right here. That tells me no x-intercepts. Yay. And finally, you'll see problems like this. A rock is thrown upward from the top of a 112-foot high cliff overlooking the ocean at a speed of 96 feet per second. The rock's height above the ocean can be modeled by the equation h of t equals negative 16t squared plus 96t plus 112. So let me just draw the picture here. So we have this cliff. Once again, don't laugh at my artistic ability here. Here's the water down here. And there's a little person up here. And it's going to throw a rock. And he throws it upward, so it's going to kind of make a parabola. And then it's going to hit the water. Okay. So now we have a visualization of our problem here. When this means I'm solving for time, t. When does the rock reach its maximum height? In other words, what is my t value at that vertex? So let's go ahead and do part A. I have h of t equals negative 16t squared plus 96t plus 112. And I'm wanting to know, okay, so every point that's generated by this function comes in the form of t, h of t. So I just need to know the x-coordinate of my vertex. My h, I'm going to call it t. We'll just know that this is my vertex I'm talking about, because I don't want to have that another h there. So my t for the vertex is negative b over 2a. In this case, that's negative 96 over 2 times negative 16, which is negative 96 over negative 32. Good thing it came out positive because we don't have negative time. And I'm going to go ahead and get a decimal for this since we are talking about a real life situation. 96 divided by 32. Oh, it's not a decimal. It goes evenly. So 3. In other words, and this is per second, so my answer to A is, when does the rock reach the maximum height? It reaches it at 3 seconds. All right, part B. And this is our last slide, by the way. Part B. What is the maximum height of the rock? So that's asking for h of t of the vertex. So I just need to plug in 3, and that's negative 16 times 3 squared plus 96 times 3 plus 112. Okay, 3 squared is 9, so that's negative 16 times 9. And let's see, 96 times 3 is positive 288 plus 112. Negative 16 times 9 is negative 144 plus 288 plus 112. Okay, negative 144 plus 288 plus 112 is 256. So this means that at 256 feet high, my rock will be at its highest point. And finally, so we're solving for t again, when does the rock hit the ocean? Okay, so you have to be a little clever here. H of t is standing for the height above the ocean. Well, if the rock hits the ocean, that height is equal to 0. So you're solving the equation here. So for C, we have 0. I want a height of 0 above the ocean when it hits the ocean. 0 equals negative 16t squared plus 96t plus 112. And I'm just going to go ahead and use the quadratic formula for this. So t is equal to the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. T is equal to negative 96 plus or minus the square root of, okay, 96 squared is 9216, and then 4 times 16 times 112 is 7186. So plus 68 all over negative 32. So t equal to negative 96 plus or minus the square root of, okay, 9216 plus 7168 is 16384 divided by negative 32. Okay, I'm going to come up over here to finish this one. T equals negative 96 plus or minus, okay, let me see if that's a perfect square. Square root of 16384. Oh, it is. Awesome. Plus or minus 128 over negative 32. Okay, now we have a plus and a minus. So I have negative 96 plus 128 over negative 32. And that is equal to, okay, 128 minus 96 is positive 32. So this is 32 over negative 32, which is negative 1. We are talking about time here in seconds. So when does this thing hit the ocean? There's no such thing as negative time. So you don't even have to consider this answer. Let's go see what the other one gives us, and that will be the time that we're needing. Negative 96 minus 128 over negative 32, and 96 and 128 make negative 224. So that's negative 224 divided by negative 32, and that gives us 7. So the answer is 7 seconds. That's when that rock is going to hit the water. And that's all I've got for you for this section. I hope this was helpful, and enjoy doing all this work with parabolas and quadratics.